All right, we're back. We're on page 187 of math analysis. We're talking about parametric equations. We now know how to write parametric equations to take an object from a certain point and have it end up at another point in a specific amount of time. And that's a big deal. Once we know how to do that, we can answer other types of questions. So specifically, we can answer things like when and where do certain things happen? In particular, what if the paths of two objects cross? When do they each reach the intersection point? How close do they get? Like a lot of things like that. So one thing people worry about is like, won't they, because their paths intersect, won't they get there at the same time? Like, no, that's insane. That definitely won't happen. Like think about every road that you've ever seen, right? There are crossroads and two cars on those roads don't necessarily hit each other, but they might both go through the intersection at different times. How close were they to hitting? These are things we want to answer. So let's see if we can start doing that. So first, we have two objects. We have object 1 from here to here in 8, object 2 here to here in 12, starting at the same time. That's going to be relevant because eventually they're going to start at slightly different times. Like you just keep layering in more things, but you think about it as you go, you'll probably be okay. If you practice, you'll definitely be okay. If you only think about it, you'll probably be okay. So let's write for object 1. So I'm going to use subscripts. So you start at 1, 5, and then you have to pick up 8 in 8, and then you have to lose 2 in 8, and you're only valid between 0 and 8. Okay. And then here, you're going to start at 4, -2, and then you're going to pick up 2 in 12, and you're going to pick up 12 in 12. But that's only valid between 0 and 12. So there's all kinds of questions we can answer. Like if they, well, don't worry about it yet. I was going to say, if we find the times that they both get to the intersection point, and for object 1, if the time is outside of 0 to 8, then like it doesn't actually get to the intersection point. It's just like algebraically the two lines will intersect, but like in terms of the motion of the objects, like they're not at risk. We don't need to think about that yet. Also, we're going to play in GeoGebra, see if we can work this out. So let's actually just do that first, because I think it's a little easier to just see it happen and then kind of like think, well, all right, how would I solve this? So what am I going to do? I'm going to start. So I'm going to do this in a slightly different way than I've been doing it. I'm first just going to write in the curve. So curve 1 plus 8 over 8 is actually 1. So I'm going to simplify that. And then 5 minus, I'm going to simplify this. So I'm doing this because it's just easier to type. V is the parameter. I'm going to go from 0 to 8, right? And then, so what I can do is I'm just going to say like, what's a of 0 and what's a of 8? And you can see GeoGebra is going to put points at those values, which I think is a really good deal. I'm also going to turn off labeling because there's just, it always labels everything and it drives me nuts. I don't know. I don't want everything labeled. I don't know why. Like it's probably a bad habit. Like here, there's no reason necessarily for this to be labeled. So let's hide that label. A and B are totally fine. So let's do another curve. 4 plus 1/6 V and -2 plus V. V is the parameter. We have to go from 0 to 12. Okay, so let's do B of 0 and B of 12. So you can see it didn't label those, which like I didn't want it to, so that's kind of okay with me. And now I'm going to turn off this label. So I'm just right-clicking and then turning off labels. All right, so now what I want to do is I'm going to make a slider. I'm going to put a point on the first curve, so I'm just going to do A of t. And it should create, let me create a slider first. T equals 1. Okay, and now I'm going to do A of t. And I'm also going to do B of t to put a point on the other curve. So I need this to go. So maybe I need to like clean these up a little bit, but let's go from 0 to 12. And everybody go to your starting points. And maybe I will turn on the label for this. So just right click there and you can show the label, and here show the label. I think I want to change this one. I'm going to make this one be the minimum of t and 8 because it's supposed to stop. So here we go. Ready? Let's see. So you can clearly see that the paths intersect. Point E gets there first, then point F gets there. So we want to answer two questions, right? We want to answer, it takes forever. We want to answer the first question, where do the paths intersect? And then the second question is, when do they get there? So we can like almost figure that out. Like object 1 gets there at like 4, I think, at 4 pretty much. And then object 2 gets there at 6. So it looks like object 1 gets there at 4, object 2 gets there at 6. So like we could find how far apart they are when object 1 gets there, how far apart they are when object 2 gets there, but neither of those is probably the closest that they get to each other. Like that's probably right around here. So that's an interesting question that we're going to want to try to answer. But let's think through what we're going to do now, right? So let's go back to the notes. We like know the answer, right? It's 4 and it's 6. I didn't look at where they were when that happened, but that's okay. So what am I going to do? I am going to use a method where I'm going to find when they get there first. Whoa, what? So we're going to find when they get there first. And the way we're going to do that, because I think that most people, like your inclination, coming from an algebra background, is to actually find where they intersect first. But that's not really the greatest way to do this when you're dealing with parametrics. So to find when they get there, think about it, when they're at the intersection point. So at the intersection, I know that x1 comma y1 has to equal x2 comma y2. Like that's the only way that can work. The question is x1 of what and x2 of what, right? So we're going to use what are called dummy variables. So I typically use t and v. You could use t1 and t2, which is probably actually a better idea. And so maybe I'll actually use that here. But I'm just going to tell you that like on the calculator, I'm probably going to use t and v because it's just a little bit easier. So what I'm saying is I have the system of equations. So this is going to be a system. It looks like parametric equations, but it's actually a system of equations. x1 of t1, that'll be the time that object 1 gets to the intersection, should be equal to x2 of t2. And then y1 of t1 should equal y2 of t2, right? So let's say t1, t2. Those are our dummy variables. So I'm going to solve this system. I'm going to let the calculator do it. So let's go to the calculator and see how that will work. Because like I just don't want to do it by hand. Also, I kind of know the answer, which like doesn't help at all. I'm going to do something weird. Go to the graph page. Like, why am I on the graph page? I'm on the graph page because menu 3, option 4 for parametric. It's so much easier to enter everything here and just have it defined. So I'm going to do 1 plus 8 over 8t, and then 5 minus 2 over 8t. It doesn't even matter if you change this part because we're just going to use these on the calculator page, but I'll change it just to make it right. Okay, so I can see it. It doesn't really matter to me. Here, 4 plus 2 over 12t. I'm just using the calculator at this point because it's the easiest place to enter these equations. And like you don't have to type as much. So I'll change this even though it doesn't make a difference. Okay, so I can see there's an intersection. You cannot find the intersection of parametric curves. It's like too complicated. So like you need another method. So what I'm gonna do, doc4, I'm gonna insert a calculator page. Do menu 3, option 7, I wanna solve a system. 2 equations. My variables will be t1 and t2. Okay, and then what I wanna do is press the var key. So that's the magic. That's why we did the thing on the graph page. It's because now all of those equations are already there. So I want x1 of t1 to equal x2 of t2. And also I want y1 of t1 to equal y2 of t2. I'm gonna press enter. Okay, and it tells me T1 is 4 and T2 is 6. So I'm actually going to write that down on the notes. T1 is 4, T2 is 6, which just confirms what we got from GeoGebra. Like, we already knew that that was going to happen. Where is the intersection point? So what I'm going to do, I usually put these in like a vector. You don't need to do this. I want to do x1 of T1, and I want to do x2, y1 rather, of T1. And then such that, and you can just put this whole thing, it's going to ignore the T2 part because it's not used. We get 5, 4. Now I want to check this, so I'll just go up here and change the 1s into 2s just to make sure. So I should get 5, 4 again. So this, what? Oh, I got it. I got to turn all my 1s. Oh man, I was like, do I not know what I'm doing? Here we go. This was in error. You see what I did wrong there? I did x2, y2 of T1. So what I did was, when object 1 is at the intersection point, which is 5, 4, object 2 at that exact time is at 14/3 2. That's what I found. Okay, so we can see the intersection point is going to be 5, 4. That's terrible. You don't even need to know what I'm doing. Oh my God, it's all falling apart. Is 5, 4. Saved it. You'll never even know. Okay, so let me go back to the notes so you can see what I've written there. And then what I think I'm going to do is I'm going to blow through this next point, the next problem potentially, in like short order just to show you. So we were able, so T1, so the intersection point is this. I think this actually is not a good answer right now. So what we should say is object 1 at intersection, and then here object 2 is at the intersection. So the intersection is 5, 4. They get there 2 seconds apart, so like they're never really in danger. So let's see if we can do this one. We'll use a calculator kind of to speed everything along. So same idea, we're gonna have an x1, a y1. So it's gonna be 0 plus 9 over 1.5 t. So you probably have the question, like, does it matter if it's in hours? Doesn't matter if it's in hours if they're both in hours. If one is in hours and one is in minutes, you decide, like, which one do you think is the best? And just commit. So this, I have to gain 12 and 1.5. So like my answers here are going to be in hours instead of seconds. X2, Y2. So it's all about writing your equations. And then once you have your equations, you're going to go to the calculator. So this was 0 to 1.5. This is 0 to 3. Okay, so what I'm going to do now is I'm going to solve x1 of T1, x2 of T2, y1 of T1. So if they get there at the exact same time, you know what's going to happen? T1 will equal T2. That's it. That'll be like, ooh, the big reveal, which may actually happen here. I don't know. But so the units don't really matter. So how am I going to do this? I'm going to like really cheat here. I'm going to insert a new problem. I'm going to do graph page, do menu 3, option 4, and then I'm going to type these in. So it's 9 divided by 1.5 t. That's weird. And then 1 plus 12 divided by 1.5 t. Not even going to change that. 9 minus 9 over 3t, and then 0 plus 27. This is what happens when you don't think. Like, a lot of that simplifies, but not going to bother. Okay, so we can see it's definitely an intersection. I'm going to insert a calculator page. And now what I'm going to do, if I can, which I think I can, I'm going to click over. I'm going to just borrow this. So Control C. This may not work for me. Control V. Oh, it did. Awesome. So x1, x2, y1, y2 are the same values that I entered here, right? They're for the new problem. But I was able to copy and paste the equation, the solving, from the other one. So here we get, they're both 1, right? So now, if I do x1 of, let's just do of 1, and y1 of 1, and then x2 of 1 and y2 of 1, that should also give me the 0.69. So the time is 1, they both get there at the same time, and the intersection point is 6, 9, they crash. This is not great for them. So these two objects have crashed. So this will give me T1 equals T2 equals 1. And then if I do X1 of 1, Y1 of 1, that equals X2 of 1. And well, that's closer to the edge than I thought it was. And Y2 of 1. And both of those give us the 0.69. So at T equals 1, both objects are at the ordered pair 6, 9. So they actually crash, and that can happen. All right, so I'm going to end this here. That's how you can figure out like intersection points, the where and the when. You really find when first. It's a very parametric way of thinking, but I'll be back in the next video, and we will keep doing some more stuff. So make up some problems, practice. I'll see you in the next one.